Hi, thanks for taking the time to watch this video. My name is Tenavi, and I'd like to tell you about some work I've been doing with my advisor, Gong, and our collaborator, Kang, on designing machine learning methods to do optimal feedback control. So we'd like to design feedback controllers for high-dimensional nonlinear systems. In this talk, we'll focus on an example from control of PDEs, but we can also try to apply these methods in aerospace or control of power grids, for example. So the control problem we're going to solve today is a infinite horizon quadratic regularization problem with nonlinear dynamics. This is a natural problem setup in, say, regularization or set point tracking. So the mathematical framework for doing this is the Hamilton-Jacobi-Bellman partial differential equation. So this is a partial differential equation whose solution is the value function v. That's the optimal cost to go starting at some point x. And if we can solve this, then our optimal feedback control will depend on the gradient of that value function. So this is really nice, but this is a nonlinear PDE with the same dimension as our state space. So when the dimension gets large, we run into the curse of dimensionality. And this has really prevented us from using this framework in a lot of practical cases. So what can we do? Well, the first option is linearization, right? We can linearize the dynamics about the equilibrium, solve the algebraic Riccati equation, and get our LQR value function approximation. It's a quadratic function here, and a LQR controller, ULQR here, which is a linear controller. So this is really nice, has a lot of successful applications, but it is suboptimal. And in the worst case, it might only be locally stable. So a lot of people have been trying to do better and develop methods to solve that full nonlinear HJB equation. I won't really go into these, but so please see the references in the paper. The one that I will go into, and I'm a little bit biased in my choice here, I'll admit, is supervised learning. So we like to think that, or we believe that this is a promising way to mitigate the curse of dimensionality, right? So we can't solve this HJB directly, but we'll try to do with supervised learning is take a detour through Pontryagin's principle. So this is a 2-point boundary value problem. We solve forward for the state x and backwards for the costate lambda, given some particular initial condition x naught. So if we do this, then we can get the optimal open loop control as a function of time, which actually turns out is an evaluation of our closed loop feedback optimal control. And also along that open loop trajectory, we can get the value function, and we know that the gradient of the value function is actually equal to the costate. So if we solve a lot of boundary value problems for different initial conditions, this gives us a data set from which we can try to learn a model of the value function. So there's been some work on doing this, for example, with neural networks, sparse grids, or polynomial regression. And these have shown some success in the past. So the nice thing about this is once we have our value function model, we can then implement our feedback control based on its gradient. And this is the route that we'll take today. Okay, let's start with generating data. We can randomly sample an initial condition x naught and solve that 2-point boundary value problem up to some finite time t. It is an infinite horizon problem, so we'd like to try to approximate our infinite horizon problem with that finite horizon. To do that, we want to check that we've reached an equilibrium and that our running cost is sufficiently small. If not, then we need to increase our horizon and try again. But if it is small enough, then we're happy and we'll put it in our data set. And our data set is going to look like inputs, x, the state, and corresponding outputs, v, lambda, and u, which are the value function, the costate, and the optimal control at that point x. Right, you'll notice t has actually disappeared here, and that's because in this infinite horizon setting, we can throw out time once we're done solving the problem. And that's really nice because we get a lot of data points for every trajectory or every boundary value problem that we solve. So this approach we call this causality free, in that it's independent from solving nearby problems. This is really great because then you don't need a mesh, potentially allowing you to do this in high dimensions. The method is parallelizable. We can generate data where we want to generate it if we're specifically interested in certain regions. And also we can generate independent data to validate the accuracy of our method. Okay, so that's the data generation. Let's talk about our model structure. So we'll call this QRnet, which is a combination of a neural network and LQR. The neural network in the past has been shown to give us good performance in terms of approximating the value function well, and then thereby giving us a good control law. The LQR, which we're adding now, will give us some sort of robustness. And I put this in quotation marks because I think robustness has a specific meaning in control, but here I'm using it to refer to robustness during training, and then also the stability of the final controller that we get. And here, I do want to point out we're not putting the straight quadratic LQR value function in there. We have an extra parameter C, which we can learn, that governs exactly how strong this term is going to be. For very small C, you basically recover that LQR plus the neural network. For a very large C, then the influence of the LQR drops off away from the origin, where we would like the nonlinear part, the neural network, to take over. This is helpful for highly nonlinear problems where we only have LQR being a good approximation very close to the origin. Okay, so we have our neural network structure. Let's train it. We have our data set, which again consists of inputs X and outputs V, lambda, and U, and we'll minimize loss function that depends on all this training data. The first term is just standard regression to match up those value function data. The next is trying to learn the costate or the gradient based on this data. And this is a form of physics-informed regularization, where we're taking the problem structure into account and learning the shape of the value function and not just fitting points. Finally, we try to match the optimal control at each of these data points, which works directly towards our ultimate goal of having a good controller. Finally, once training is over, we can validate the network with an independently generated data set. This gives us an empirical measure of how well the model performs on this unseen data. And this is a nice feature of this causality-free method. Okay, so we've seen how to generate data, we've looked at our model structure, and now we know how to train the network. Let's see how it does. The problem that we'll look at today is a unstable Burgers type PDE. We got two inputs. They're active on these blue regions there. And then we also added in a destabilizing reaction term that makes this a little bit harder to solve. We turn this into a system of ODEs with Chebyshev collocation. We have 64 nodes here. And we need a lot in order to represent the dynamics well. But with 64 nodes, it's a really high dimensional system. Fortunately, we were able to solve this problem, and we'll look at that now. Okay, so we've looked at data set sizes of different data sets of different sizes with different number of trajectories. You can see that plot on the x-axis. Each of these trajectories, again, has a few hundred data points in it. And for each data set, we'll train both a standard neural network in blue and a QRnet in orange. And we'll repeat each of the experiments 10 times to sort of account for randomness in the data generation and the neural network training process. So here we can see that compared to LQR, both of these neural network methods do quite well, especially as you increase the data set size. And the other thing that we see is that QRnet does a little bit better than the neural network, especially when the data set is small. And this is going back to that robustness that I talked about earlier, because we see that QRnet tends to be less sensitive to variations in those data set, which happens more with small data. The other thing that I want to point out is that the training time for these is quite short, just a couple minutes, which is advantageous in a iterative controller design process. Okay, so this gives us an idea of how well the overall kind of accuracy is of the network. But one other thing we're interested in is stability. And so here we're just plotting the largest eigenvalue. And one of the things that kind of shocked me was that for the neural network, a lot of these are unstable. And here we really see the advantage of QRnet, because even if the performance isn't that good, or the data set isn't very large, you can still rely on this to be stable. So now we have the comfort of knowing that when we're training, we don't have to worry about stability. We're just trying to improve the performance. And that's, I think, a real advantage of QRnet. Looking at this from another perspective, If we take two neural networks, one is the neural network, one is QRnet, and we control the system for many different initial conditions. I'll plot the norm of the initial condition on the x-axis, so bigger norm to the right. And then the y-axis is the extra cost accumulated relative to the optimal trajectory. So both neural network and the QRnet outperform LQR, especially far away from the origin. But one thing I want to point out is that the neural network has a couple outliers where it accumulated a lot of extra cost, even though it started close to the origin. And that's just because of that unpredictable nonlinear structure of the neural network. In QRnet, we don't see this because of that extra LQR component that gives it a little bit more stability. So let's just finish up by looking at some closed loop simulation. Here we can see that QRnet is doing a nice job stabilizing that Burger's PDE. You have the two control profiles where QRnet closely approximates the optimal, even when the LQR is not actually close there. And to summarize what we talked about today, both QRnet and the standard neural network do better than LQR. QRnet does better than the standard neural network in terms of robustness during training and the stability of that final controller. And all in all, we think that the supervised learning approach mitigates the curse of dimensionality and gives us a potential avenue to design feedback controllers for high dimensional nonlinear systems. So in current work, we're trying to now analyze the stability of these neural network controllers more thoroughly and extend this framework to solve more realistic problems. And if you've made it this far in the video, thank you so much for watching.